Okay, so we are starting on refrigeration, the actual chapter or the name of the actual subject. I realize that we don't have a lot of time to make it all fancy and big. There's so much to learn within refrigeration itself. But yeah, so it'll be chapter 11 in your textbook. Let me just confirm that your single textbook. I'm just looking for it quickly. Just give me a moment. I'm making sure chapter 11. And if you were to practice all of that, all the good questions at the back of that book, you should be more than adequate. That's not a difficult section. Students normally score, at least chapter 11. Then they're normally quite good at this. So please ensure that you really spend time and master this section. It's not difficult at all. Okay. So before I start, and hopefully I can engage a few people, and maybe your brain's not all there. You guys remember the Rankine cycle in thermos 2, right? And also do you remember that it's a heat engine? Who remembers the Rankine cycle? Basically, it was steam plant. You know, when you have to work out your thermal efficiency of the you've done it. Who remembers this? So I have a lot of students here. Mr. Basson, Mr. Doyle, I think they was all there. Mr. Abril, do you remember this? Okay, anyone? Mr. Matoso, Mr. Neto.
Yes, I do remember. I just remember that I solved a lot of problems of this, but now yeah. When I did my S2, yeah.
Yes.
Plant, yeah.
Okay.
Yeah. But now.
Great. But now what? You're
I have to go back, yeah.
Yeah, no, it's fine. So you can understand why I'm introducing this thing. So one thing is important to look at the processes, right? From 1 to 2, we've got a compression in the pump. From 2 to 3 there, we've got the heat addition in the boiler, right? From 3 to 4, we have some kind of expansion to the turbine. And from 4 to 1, we have some heat rejection in the condenser, right? Obviously, the schematic is saying it. And also, in keeping with that, we remember what I talked about in the first lecture of thermal cycles of the power cycles. A heat engine uses heat and provides mechanical work, right? Uses heat and provides mechanical work, right? So this is what a heat engine is. Our heat in is a boiler and the work out is a turbine, right? And obviously the turbine will spin a generator which produces electricity for us. That's one application for steam, right? Obviously there is other ways of looking at it. But what I want you to be aware of is look how it flows. 1, 2, 3, 4, right? How it flows. Okay. Now let's start moving on. So just remember this, right? The cycle. Okay. Okay, this is obviously our test dates. This is just an announcement. That's fine. So before we start the refrigeration, I want to include a whole story about microorganisms and why we do refrigeration. But just kind of keeping it concise and straight to the point. And it says a major application area of thermodynamics is refrigeration, which essentially transfers heat from a lower temperature to a higher temperature. Now that's very interesting. If you look at the first law, the second law of thermodynamics, the law of entropy, you find that temperature always goes from a hot to a cold. That's how normal temperature travels. And we'll be doing it in the next section in heat transfer, right? But what a refrigerator does is essentially it's a reverse heat engine. Anyway, so it says devices that produce refrigeration are called refrigerators. We all should be aware of that. And the cycles on which they operate are called refrigeration cycles. Particularly what we're looking at is the vapor compression cycle. There's also the vapor absorption cycle as well. So the most frequently used refrigeration cycle is the compression refrigeration cycle, in which the free refrigerant is vaporized and it condensed and alternately is compressed in the vapor phase. So we'll unpack the most important cycle there. Also, it says I use the principle of latent heat, which basically at phase changes liquid to gas, and which basically results in a large absorption of heat. Furthermore, in refrigerators, let's say this phase changes is okay. It's fine, right? So we'll talk about that. So two things, right? We are taking lower heat, and we're taking it to go from a low temperature to a high temperature, which I think is over here, right? Which explains that. And other one was, yeah. So looking at this is, if you remember a heat engine works in reverse. So I think I want to actually to get the actual heat engine slide from the previous the previous what is this the lectures. And you understand why this is kind of important. It is a bit of some background, but it is useful to understand. So I'm just opening up my auto cycle one here, I think. Oh, just bear with me. The heat engine. Okay, it's basically this over here. So I'll just copy it and I'll just paste it here. Cool. Yeah, so I'll place it over here, right? So again, looking what a heat engine is, we are taking a hot source, putting it through a thermodynamic cycle. Obviously, the temperature decreased through that. Obviously, we need two temperature sides. I did mention this. Obviously, there must be some gradient, and we get a work out. So what happens in a fridge? It's also called a reverse heat engine, right? And in this case, we put work into the system, and then work facilitates the movement of a low temperature to a high temperature, right? And this is very important. So also to note, it's the same principles air conditioners work on, and I'll unpack that briefly as I go through. So I want just to make you aware that a fridge is a reverse heat engine. So a heat engine takes heat, we get work. In this case, we're putting work in, and we're moving the temperature. So just as a quick thought, think of your fridge at home or freezer at home, and I'd like to ask you, where do you think the work is coming in? What is producing the work in a refrigeration cycle? I just want to give everyone a minute to kind of think about that. Megs, Ms. Macholo, what gives the work? I am Mr. Pereira. I hope you guys are listening here, eh? We're just thinking about Navok. Hi, sir. Yes, expert thermodynamic professor, Mr. It's the compressor. Yes, beautiful. So that's a good start. Okay, so let's quickly see. So this is basically just a basic setup of what's happening here. Or just basic explaining, I guess the idea. So let's say number one, if our interest in food preservation, we keep the food in TL. Obviously, this is from low temperature to high temperature. This is the system you're looking at. This is kind of like a additional thing. If our interest is the warm environment, we use it to deliver it in TH. So maybe that could have been maybe keeping your for instance, you can keep your room warm. That's through air conditioning. And if our interest in a cool environment, we wanna pass our unheat through. So this is like a really bonus slide. It's kind of redundant in my opinion with this kind of thing. So let's quickly talk about some refrigeration applications, really. And I mean, obviously, one wants to really explain the cycle before they get here. But refrigeration is a very important field for mechanical engineer. We've got high temperature refrigeration, medium, low. We even got cryogenics. And normally high temperature stuff is basically used in the air conditioning industry. And we're talking about the lowest refrigerant temperature around 2 to 5 degrees, and we're keeping air around 15 degrees. So that's the stuff that we normally used to. Medium temperature is using food conservation, basically keeping your food cold, and it's around just above 0 degrees, about 3 degrees, and always, obviously, it goes as low as minus 12 to 8 degrees, depending on what. And we have low temperature, like very extremely, so we will take things further, and this is more for industrial processes, maybe we're keeping medicine, or maybe freezing, not medicine, but keeping things much more colder. Maybe people going to preserve their body, obviously not that. And we have cryogenics. So cryogenics with liquid nitrogen is normally what you're looking at, but very, very cold temperatures in the region of 196 degrees. So refrigeration is a very useful thing. Obviously, for the maritime thing, you guys obviously heard of a reefer, which is a ship which carries a lot of containers, or refrigerated containers. I'm sure you heard of that. I'm not sure if there's anything else or what's important in maritime application. Obviously, the reefer itself has all the components we should discuss. So has anyone worked with refrigeration? Has anyone changed compressors, condensers, evaporators? Can anyone just share a brief experience on the maritime applications of obviously some of you guys have experience. Let's have a look, Mr. Passon, Aaron, Mr. Neto, Mr. Matoso, Mr. Trele, Silas, also seasoned maritime. Anyone deals with refrigeration? Is it something you require to know? Is it important? Hello?
Sir, Mr. Abreu, you need to know
Yes.
the right refrigerant to use for the
Yes,
specific compressor. Yeah, you need to know the right refrigerant to use. Yeah, the right gas.
Okay, that's correct. The right gas. Yes. Anyone else? That's a very very important. Ernest. I know Mr. Manas went for a refrigeration course recently. Was it 2-3 months ago? Mr. Manas, you know, maybe share what you've done there. Don't know if Mr. Doyle is you guys are there. I'd like to hear what you've done. We had a brief discussion on it. System parameters. Can you please elaborate? I'm just trying to initiate a conversation on if it is important to know or not important. Okay, guess no one has anything. Megs, I think that's Megan. Did you work on any refrigeration at all, or air conditioning even? Mr. Gabriel, I'm sure you have something to say. Let's see. No, only installation. So what do you install? Can you just maybe talk to us about that? You're gonna type. Okay. Cool.
Yeah.
Yes, go for it.
Yes, I've worked on refrigeration system, like as a third engineer. Like once we change, I've changed compressor.
Beautiful.
Yeah, I've cleaned the condensers. I've worked
Yes.
a lot on this, on the refrigeration system. And once we had a problem with the compressor, and yeah, and like for example, in the refrigeration room, like we used to store the, how can I say, it's the oil for the compressor.
Yes. Yes.
Yeah, and that oil was not supposed to be used on the compressor, but was stored on that room. And there was a new chief engineer. He was a new on the boat, and
Yes.
he used the wrong oil on the compressor.
Yeah.
Yeah. And then we had a problem. We work for oil company. We have a support from shore, and then
Yes.
the compressor was broke. We called
For sure.
we called the technician. And when the guy came, like we didn't know what exactly happened, but it was the wrong oil. And then the guy, yeah, I think they brought a new compressor, and we had to put, we had to put a oil, and they were giving that wrong oil again. And the technician just saw the oil. He could not, no, this is not the oil. And then we use this oil. Hey, he was saying, oh, the problem was that. And then chief engineer was feeling so bad. I broke the compressor. I used the wrong oil. Yeah.
Okay, no, great. Okay, so you've opened my eye to something which I actually wanna. We check parameters, pressure, temperatures, and add freon. Okay, so that's nice. Thank you guys for that. I just wanna write something down because maybe on Friday I'll share with you some. Obviously, our stuff is gonna be analysis, but I wanna write something down for you. Okay, checking parameters. Yeah. to see maybe what is useful to you. And compressors. Obviously, the compressor is the main guy, right? Okay. Compressors. Okay. And maintenance. Okay. Cool. Yeah. I'll pull up. Yes.
Just one more very important item on the system, on any refrigerant system, is the thermostat expansion valve. You need to control that one. So because that one is the main component that controls the flow of the gas on the system. And
that is correct, yeah.
Normally, it gives you indication on how the system is behaving. If it's good, if it's missing gas, if the gas is okay, if it's too much gas in there. So the thermostat expansion valve will give you indication of that. It's a very important thing also.
Yes, no, for sure. Thank you. Now. Okay. Cool. So, Mr. Brew, thanks for that. You see now, okay, that helps now. Okay. Yeah, anyway, so you guys are aware of refrigeration, right? So let's go to the thermodynamics. We're gonna talk about. I'm just getting excited because I'm thinking of the other resources I actually wanna share with you guys. But anyway, so when we're talking refrigeration, what's important to understand, they're saying, okay, yeah, we're kind of shooting over a bit here, and they're saying vapor compression system. So in someone's gonna ask you what cycle this thing runs on, it's called the vapor compression, right? And there's a reason why it's compressing vapor, and we're gonna unpack that now, right? And here they're saying, and cooling is accomplished by the evaporation of a liquid refrigerant, or the gas, as Bruce called it, under reduced pressure and temperature. And the compression and a VCC or refrigeration, the compression cycle consists of 4 components, right? A compressor, you're aware of, a condenser, an expansion valve or thermal expansion valve. Obviously, you can use a capillary, depending, fridges have capillary tubes, and then evaporator, right? So that is just the start of obviously the basics of what's happening. Okay, so let me explain how this works for obviously for the people who's not aware, and then we can actually well, I have to probably do a bit of extra digging deep time to make it a bit more relevant. Yeah, anyway, so where it all starts, right? So we can start at, we start at the compressor. Let's start at the compressor, right? So what happens with the compressor? The fluid or refrigerant enters the compressor where the temperature is elevated by mechanical compression, right? So that is not true. It's not the fluid. It comes as a gas, right? So just call it the fluid. So I'm gonna say the refrigerant, rather. Let me call it the refrigerant here. Just so I can have peace in this text. So the refrigerant, right? Right? It's not a fluid. It's not a gas. It's a refrigerant. Yeah. And I've got a better slide. Obviously, you'll see the slides now, right? So it enters as a gas. What happens? The compression raises the pressure and the temperature of the refrigerant, and from there it goes into the condenser, right? From the condenser, what happens is that the gas now condenses back into liquid form, and it basically releases heat to the surroundings, right? We'll talk about what's happening there. Unpack it now with a domestic fridge. Furthermore, your refrigerant is still at a high pressure. So as it goes to something called the expansion valve, where the expansion valve basically takes the high pressure fluid and drops the pressure back to lower. And the reason why we do this, and once it's, then the low pressure fluid goes into the evaporator, and within the evaporator, what happens there? It absorbs heat from the surrounding environment, right? And basically, it goes from a liquid back into a gas, and then from there, it re-enters the compressor as a gas, where it gets compressed into a high pressure and temperature, goes to the condenser, it goes from a gas to a liquid, obviously it's condensing, goes back to liquid, it's a high pressure liquid, from a high pressure liquid, it goes to expansion valve to reduce the pressure. So, I'm just obviously repeating it, and it does that the whole time, right? Obviously, if it doesn't do that, there could be some air in the system, the gas is leaking, you don't have enough charge on the system. There's a few other things which just could happen. So just to explain to you, maybe, if you just imagine your domestic refrigerator, maybe I should use this one. That black box, right? And all refrigerations are the same, whether it's domestic or even in the industrial. The black box, obviously, as a compressor, if you have a look over here on this, you can see the motor, which is coupled basically to the compressor over there. You can see those motors there in this unit. I have a better diagram for that. That's the compressor. The black part of the fridge or behind the fridge That is a condenser. That is why we feel at the back of the fridge, there's a bit of heat, right? You might ask, okay, there's also another small tubing, which is called a capillary tube in fridges, and that is your expansion valve. So you have different kinds of expansion valves, different kinds of condensers, different kinds of compressors. Now, unfortunately, the purpose of the course is not to unpack each device, but I might have an extra slide maybe on Friday to kind of maybe unpack it more in a more maritime kind of thing. Talk about the specific equipments. Furthermore, you might ask where your evaporator is. Your evaporators are hidden within your actual fridge. So your fridge, where your food is sitting, the evaporator coils are there. So that is responsible for extracting the heat from the food, in fact. And then what it does, it basically rejects the heat at the back. So the heat you're feeling behind the fridge, that's the heat from the food you've put in, or the environment itself. So is it all clear to everyone? Or was it explained well, I mean, as a layman, for everyone to understand? Can you get a few thumbs up? Is there any questions on how a fridge works or refrigeration cycle? Mr. Matoso, Mr. Gabriel, what you think of that? Good explanation, thanks. Yep. Just as a layman, obviously, as an introductory level kind of setup. Okay, thank you. If there's anything you want to add, you can maybe say it. Because what I want to make you aware of this particular chapter is only a standpoint in showing you the design of refrigeration cycles. If you want, I can share a book with you to show you how big this thing is. So this is just the introduction in refrigeration. In fact, in my advanced diploma or BTech, I had a module called refrigeration and air conditioning where we exclusively focus on the design components. Obviously, in Thermos 3, which we are doing, just the introduction to how the cycles work. So I'm just making you aware, right? Obviously, yeah, anyway, let's just not talk too much on that. So again, same setup. At point number 1, I like this one because obviously it's animated. So we get a low pressure liquid refrigerant in the evaporator, and it absorbs heat and changes into a gas. Now I want to ask, why is it a low pressure liquid? Why do you think it's low pressure? Why low pressure? Anyone? You guys perhaps know. Okay, it's fine. Maybe you'll unpack it later on. There's a small pot in refrigeration. Afterwards, it goes into the compressor. They're saying it comes as superheated vapor. I'm just dropping it into the compressor. The pressure and temperatures, obviously pressure and temperature is linked to each other. Furthermore, we get into the condenser. Is that a question? I don't know what that was. Okay. Furthermore, get the condenser. So we have the gas gets rejected back into high pressure liquid, and we have an expansion device. Could be a thermal expansion valve, which not only reduces the pressure, and as Mr. Brill said, it controls the flow. It's a regulator of some sort, right? You can tell a lot from the expansion valve. Okay, so this is a domestic setup, and I just basically put that thing there to show you where everything is. I think I explained it that here we have the black box, which is the compressor, the condenser coils at the back, and inside the fridge is the evaporator coils. I explained that. Obviously, for the maritime application, you've got your container, and I'll talk about that. And over here, you get different kinds of shipping containers. In particular, you get a closed reefer container, you modify control atmosphere, and you get automatic fresh air management one. There's a few of them, and obviously they depend. When it passes through the expansion valve, yeah, the pressure is lowered. Yes, that is definitely correct. Yeah. It obviously must come as a low pressure refrigerant, and there's a specific reason why. So making you with these different containers, and obviously the ones normally closed reefer, and this is probably the one we look at. And when we design these containers, one would be cognizant of a few things, but one where you're looking for the actual components is over there. You get a picture to your right. That's where that is the refrigeration system. While the main thing, as you can see, that the white thing there is probably a scroll compressor. You've got a fan to facilitate the movement of what is this? It's either extracting the heat. So one is the refrigeration unit. 2 is the boxes do not extend beyond the pallet. Okay, there's a region there. So in fact, even with refrigerated containers, one must be aware on how you structure what is this now? What am I talking about? How you place your cargo, so to say. There's a nice video actually on that, on particularly on the reefer, on the containers and stuff, and how they get the airflow right and all of that. So I'm just making way. Those are the essential components, and obviously we don't go in so much detail when we look at all these kind of stuff here. Oh, and over here, obviously it's exactly the same thing, and it's literally telling where each component is, where your motor coupled to your compressor, and so you might have obviously there's a ventilator there on top, and you've got your expansion valve, all your components are. So it's just important to be aware, you know, or what is what, and what you should expect. So, for instance, if you are not getting enough suction or not enough discharge, or maybe if the temperatures are not right, there are specific reasons as to why your system is failing. And I think I really want to touch on that maybe towards the end of our analysis part of the thing. But obviously, we're looking at a different perspective in terms of refrigeration. Okay. Yes, your vapor compression cycle is also used in air conditioning, if you didn't know that. So if you have seen air conditioner before, the indoor unit, you know, that the thing always put on the wall, that is the evaporator. That is responsible for absorbing the air inside the room, the air, basically the air on your body. Your body's radiating heat. And then in the back unit is where the condenser is, and where the condenser is, you feel the back, you know, I don't know if when you hear the fan go on, the air is coming out, and that is where you feel the heat, and also that is where your compressors are housed and all the other components is housed. The same with your car. Your car has an air conditioning system and also operates on a vapor compression cycle. Same components: compressor, condenser, expansion valve, and evaporator. There are other subcomponents like dryers and accumulators, but obviously that's not the point of this course. It's more or subject or module. It's more about the thermodynamics of how it works, or the basic thermodynamics of how it works, right? So it's important to understand the technology, obviously, when you do the analysis, right? So I was hoping someone's going to ask me a question. Sir, you said we're taking a low temperature and we're going from a high temperature. So how does the aircon work? Because the aircon can provide both heat and both what is this? Cooling. Who has an idea of how we're able to have both heat and cooling on an air conditioning cycle? Anyone? Hello. Yes or no? Never heard of it before? Anything will do. Okay, anyone? No one saying anything. Okay, so the way we do that is by something called a reversing valve. No idea. There's something called a reversing valve, right? So if someone's going to ask you, it's basically the same principle as what is this? It's the same. It works the same, but we have a reversing valve, which basically. Okay, someone's saying something. Yeah, what is the question? Oh, the question is, remember we talked about the fridge. So a fridge basically takes cold heat and then put it, and we're going from low temperature to high temperature. But remember, in terms of a air conditioning, and I said it operates on the same principle. How do we get hot? Because now we're going from hot to cold. But it's not a big thing. I just put a picture. A lot of students ask me this, and I'm just going to make you aware. When you're getting hot air, there's something called a reversing valve, which kind of facilitates the heat. So I don't want to unpack it. It's not something particularly important, but that's the technology we use so that we're able to redirect the hot and cold air, right? So you can always have a look at a video so on how that works. So probably to throw a video on the refrigeration cycle. Yeah. So obviously some people are aware of how it works. I don't know. Maybe it'll be useful. Right. And where we want to head off is the thermodynamics. The thermodynamics, right? And what we basically do is take the components, whom we make a simple schematic. Between 1 and 2 is your compressor, 2 and 3 is your condenser, 3 to 4 is your expansion valve, and 4 to 1 is your evaporator. From the schematic on the left, we can put that on a TS diagram. Excuse me, on a TS diagram, as you can see there, it's going to form some kind of thermodynamic, what is this now? Thermodynamic cycle, right? If you remember well, it's important to look at the TS diagram. On the TS diagram, you need to know where the vapor side is and the liquid side is. And obviously, that's why it's important on the Rankine cycle. And my question is, doesn't this look awfully familiar to the steam power plant, Mr. Matoso? The Rankine cycle. Does it look familiar? I'm gonna copy that picture for you here. Right? Doesn't this look familiar? Look at that diagram. Right? Some guy got rich just by thinking out of the box. Let's have a look here. You see there? Same. The difference is that at our Q out we get QL, and let's even talk about it further, right? Instead of going from, so here we go 1, 2, 3, 4, we're going the other way. So our direction is going the other way instead, right? And our components are switched. So on top we have the condenser, where normally we had Q in, and at the bottom side we have an evaporator. Obviously that's the same like the boiler. And on either end, by 1 and 2, of the Rankine cycle, we had the compressor, our pump, and obviously now we have the compressor, and obviously our turbine. It's all interchanged, So it's the same kind of it's a reverse heat engine. That is why I just basically threw that there, right? Just to make you aware, just something fancy to know. It's operating on the same concept. Okay, so when we're obviously doing our thermodynamics, we talk cycles. What is the cycles it's employing, right? So for our ideal cycle, right, we're going to start off with ideal and we're going to build up further. From point 1 to 2, our beloved isentropic compression, right? Straight line. From 2 to 3, we've got this line going up. So what you are seeing there, point 2 is superheated. If you remember your saturation stuff, maybe I should just pull that up quickly. I just like to make sure I don't want to talk over just in case you got saturation line. Obviously, water still the same. And this, I'm just gonna get a nice diagram for us. Wet region, concentration vapor. Just give me a moment. I found one, but I obviously want a better one. Maybe this one. Liquid vapor line, critical point. Yeah, maybe this one. This is a bit better. That's a bit small. So it has to be aware on the diagram what is liquid, what is what is vapor. Obviously, you guys should know that, but we always want to just recap, and you want to make people forget. So I'm just looking for a decent diagram, a general one basically. I can't find really a good one. Okay, I'll just use this one over here. Okay, copy. Just close this. So this is just obviously okay, luckily it's the same slide. I can just, this is just a basic saturation. This is of water. It's essentially exactly the same principle. And what you're looking at, obviously, at point A, B, it's liquid. This is the liquid side, and if you come in the middle, there's a dryness fraction. It's wet. It's called vapor because there's some water. And on the far left, it's called this is called a vapor. This is called a gas because it's completely. It is no more. It's completely saturated. And if you go further up, you're going to get superheated steam. So obviously, we're going to be pulling enthalpy values here. So operate on the same concept over there. And obviously, from 3 to 4, we have called throttling and expansion valve. So there's a change in it expands. However, what we normally deem that as an isenthalpic expansion, that means our enthalpy doesn't change much. Through expansion, we lose a lot of energy. It's obviously it does happen a bit, and obviously we have a constant pressure heat addition in the evaporator. So that is the heat we're getting either from the room where people are, the air conditioning, or the food itself, right? Just using the two basic applications, right? And the QH, the heat ejected, is at the back of your fridge or the outside unit of a, what is this called now again? What is this thing called? Of air conditioning. We also have the pH diagram, which is not normally used. I don't normally use it. I might use it. I doubt it. But normally TS diagram is one. So you can actually use a pH diagram as well. Important metrics. So the main point of the diagrams is to obtain enthalpy values. And where do we obtain an enthalpy values? I'll tell you shortly. Obviously, you might have an idea, but the main thing what you need to know of the cycles is the efficiency, which is also deemed the COP. And what the COP basically is, let's say the condenser and evaporator doesn't evolve any work, and the compressor can be approximately adiabatic, then the COPs are of refrigerators and heat pumps. I don't know if we touch on heat pumps, but we probably might. Also depending on time. But what you need to know, the COP is just like the efficiency of the vapor compression cycle. Remember, the efficiency is like the Otto. Basically, what you're getting out is H1 minus H4, which is the heat being removed, and what you're putting in is H2 minus H1, which is the compressor. So the vapor compression cycle, depending where you are, can be used for two reasons. You can use the heat, the QH, or you can use the QL. So depending where you are, that's the COP you're going to use. So predominantly, you're going to use the H1 minus H4 divided by H2 over H1. If you're going to use a heat pump, you're going to use H2 minus H3 because the heat rejected is the main thing. Is anyone aware of a heat pump? Just as a side note, maybe. You guys have any experience with heat pumps? Have you heard of a heat pump before? No one? Okay. Yes, Silas.
I was just thinking, can maybe the extraction fan or something like that can be a heat pump?
No, a heat pump is a completely different device. It's actually one of the most efficient water heating systems. It's basically instead of using your condenser, rejecting heat by your condenser, we actually use the heat rejected to either heat the room or to heat water. In fact, my research is based on a heat pump, particularly a solar assisted heat pump. And I know a lot of you guys know. So instead of using actually a boiler to use heat, a heat pump is a very efficient device. Now, we're talking about the COP and we're talking about the efficiency. So I want to provide a revelation for you. What are standard COP values for heat pumps? Standard heat pumps. No, for refrigerators. We know our refrigerators, right? And efficiency normally can't be more than what? Not more than 100, right? Are we aware of that? Do you guys agree? Your efficiencies are normally always less than 100.
Yes, there is always loss.
Yes, it's always less, right? But for fridges, it's always more than 1. So that means the conversion between because what it means, we put a little electrical energy in and we get a lot of thermal energy. And so the fridge itself is a very, 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 very efficient device, right? And what I mean by this is that if you look at the direct energy conversion, it's really, really efficient. You get a COP anything from 2 to 4. So what I mean is that if you put 1 unit of electrical energy, you get around about 3 to 4 units of thermal energy. So it's a very, very efficient device. So you're going to find your COPs always the excess of 1. It's minimal 1, 1.5, 1.3. Very, very important. And I should making a special note here to maybe unpack that a bit more. So I want you to know your COP is always for refrigerators always higher than 1. I can probably pull up a lot of research on it. So I don't want to go too far on that. So I'm just looking for standard values. I don't want to spend too much time. It's not giving me any good stuff here. One must probably look at some analysis on that. But I'll obviously fill up what I need to do in the next part of the lecture. Okay, so I'm making you aware. So when we're analyzing refrigeration cycles, we have to use our refrigeration tables, and that's going to be table A11, right? So if you remember your steam table or something similar to that, and what I want to make you aware of, we have table 11 and table A12, where we have the saturated table. So on the left-hand side, we have the temperature, and for table A12, it's the same thing. But here we just use pressure. So you have to sometimes use both depending on what is given. Moreover, there are 3 columns, and the 4 columns, it's going to be specific volume, your internal energy, which you don't typically use here, right? Enthalpy, definitely, and entropy, definitely. What's important, under each one, you get UF, UFG, and UG. F is denoted for liquid, right? I put this up here for you. G is for gas, when it's a saturated vapor, where it's lost on its vapor. And HFFG is the amount you have to take. So basically you have a liquid, which is completely saturated, it's the amount of energy required to take it to vapor, which is HFG. So I want you guys to be aware of that. And obviously your saturation pressure and temperature is linked. So if you compare the minus 40 degrees, if you actually look at the table at minus 40, you can actually find the correct pressure. Of course, with this, there might be interpolation involved here and there. So you obviously don't want to make it too tricky. Okay, so what I actually wanted to do for this particular thing, the things we're going to look at is our ideal vapor compression cycle, our actual vapor compression cycle, and possibly our cascade vapor compression cycle. So only 3 of them, and there's more. I did make you aware of this. Okay, now we can finally start on our first example, and I'm going to give you one to play around with, right? So this one is going to take not a long time. Guys, this section is it's very easy. It's very procedural. And if you know the procedure, you're good. They normally go for around 15 to 20 marks. Could be 15, 20, depending on what kind of cycle you get, right? So yeah. Okay, cool. So I'm just going to share my whiteboard, and then we're going to actually start solving this problem. Okay, so I'm just going to take that, go to my whiteboard. After this, we can have a small break. Then you can basically solve that problem of yours. Obviously, there's a lot of information coming in. You know, you had a long day also. Okay, so this is our first example. This is in your textbook as well. And that's on page 612. I think I have it there. Okay. So what I'm going to do, I'm just going to snip to the actual diagram so that you have, so it's on there. Okay, so welcome to your first analysis on refrigeration, right? And you can do this with your actual fridge. You can measure all the stuff, right? If you have actual parameters. Okay, so our typical question reads, just lock this, okay, it doesn't really matter now. So a refrigerator uses refrigerant R134A, and what's important, yeah, we have a lot of types of refrigerant, and I didn't want to unpack that. I got a whole lecture on different types of refrigerants, but the refrigerant of choice for our analysis is R134A. And it operates on an ideal vapor compression cycle. Keyword ideal, right? Because we're going to get to the actual. It operates between limits of 0.14 and 0.8. It's either 2 pressures or 2 temperatures. If the mass flow rate is 0.05 kilograms squared, determine the rate of removal from the refrigerator space, which is QL, and also the power input to the compressor, which is work in. Also ask for the rate of rejection to the environment, which is the QH, and also the COP of the refrigerator. All right. So first thing is first, right? We start on point 1, and I want you guys to obviously making this very interactive, so you check. So you write P. Let me just get my black pen, my white marker. P1 is the pressure of 0.14 megapascals, and what we're looking for, so we're at point 1 here, right? So which region is there a vapor or a liquid? Can someone please tell me?
Must be vapor, so to go inside the
Yes,
compressor.
vapor. Right. So what you want to do when you're at this particular problem, right? We're gonna have to go find H1 and S1. And of course, what is important to note here, guys, please, this section is 3 marks really. They are G. They are this is the vapor. This is the liquid side, or we can call it gas or vapor. Yeah, saturated vapor is obviously on the line, and this is obviously vapor over here. So we want to go look at a table at a pressure of 0.14 MPa, and we want to go collect H1 and S1. You get a mark for each of that. So can you guys quickly go check your table? Get your book out, or get your tables out. Check table. What is this table? What do I call it now? A17. So not A17, A12, and please go collect that particular HG, and you want SG. So what pressure was it again? Let me look at this. At 0.14 MPa. 0.14 MPa is obviously 140 kilopascals. So please go find it. Obviously, I'll bring it up in the first lectures or so, and eventually we'll just get used to it. All right. Let's see. H1 and S1. The reason why you're finding S1, I'm letting you know, is because S1 to S2 is an isentropic process. So let's quickly get that. It seems Pereira says 276. So what I'll do, I'm going to copy the table. Yeah. Where are we? There. And let's have a look quickly, right? 140 kilopascals. We're going to we're always taking our enthalpy values, like I said, Hg at 140 is not 239. 239 and 0.94467. 140 kilopascals, 0.14 MPa, right? Do you guys get that? Very important. Not sure how we got that. Yeah, 239, yeah. Saturated, not superheated. We're getting there. Saturated tables, right? So yeah, if you got that down, so I'll just quickly remove this. So H1, what was it again? 239. 239.19. Make sure you have your units there. Kilojoules per kilogram. And S1 is 0.944. What's it again? 94467 kilojoules per kilogram Kelvin. The units is kilojoules per kilogram Kelvin. You get 1 mark for this, 1 mark for that. Okay. So to find point 2, so maybe I should say, I know Mr. Boyer likes process 1 to 2, which is the isentropic compression. I normally used to ask some theory questions or stuff, but I just kind of gave up eventually. So to find point 2, we need to find similar stuff here, right? But How do we find 0.2, right? Does anyone have an idea? Okay, so what I'm making you aware of first, right? That this over here is now the superheated region, right? You obviously have to superheat. Remember, the compressor raises the pressure and temperature, right? Superheat, right? Con, it is superheated here, right? Superheated vapor. Okay, and what we need to do is now obviously find our enthalpies there, right? So we know that S1 equals S2, and we also know that it operates on a pressure. It also works with a condensing pressure of 0.8. So P2 is also 0.8 MPa. So what we have to do now is go to another table, right? Obviously, these tables will be given to you, and the table I want to go to is table A13, right? And this is what I didn't discuss. Okay, not didn't discuss, but so I'm gonna copy it here for you now quickly. And with superheat, what's important to note with superheat, it is coupled with both a pressure and both temperature, right? So what you need to do now is go find the pressure of 0.8 megapascals, right? Your table. Okay, so let's just quickly do that. So you're at table A13, and I'll copy my table now. It seems difficult, but it's not. I know Ernest is a specialist in this one. So you find 0.8, boom. Okay, so what you're probably missing is the top of the actual thing. So I'll just get it for you quickly now, so that you can see. Copy. Like that. So temperature, specific volume, internal energy, enthalpy, and entropy, right? And you guys find the table, 0.8. You guys get it? Students, are you still there? Hello? Guys, are there any questions? Are you guys lost? I'll give it 2 minutes here. Who's guessed? Megs, are you good? Okay, yes, I can see. Okay. So guys, so what we need to do now next is we find 0.8. So it's operating at that pressure. What we need to do is look at, so our saturation temperature here, it's given, and that's 31 point something. But thing is, we're not looking at that. So we're looking at S1 equals S2. You get a mark for writing that, and you know that is 0.94467 kilojoules per kilogram Kelvin. So that falls between here, right? You agree with me? So what that means is that you're going to have to interpolate between S and H. And obviously you're gonna have to use your calculator. So you have 0.9185, 0.9481. Just bear with me there, it's not nicely written. And obviously what you're looking for is 267.34. Mr. Matoso, I hope you can do this quickly and you can find your enthalpy. I've showed you guys how to do this, and if you can find that, you can find H2. That is what you need there. Is that clear to everyone? So use your Casio calculator. That is why I introduced tables initially, so that it's not a culture shock when it comes to you. This might be a question. Yes, Silas.
Yeah. So what take us to that to these two values? I'm a bit lost there.
Okay. So I think what I'm failing to do is that, you see, point 1 to 2, right, is isentropic compression. Do you understand? You agree with that, right? Straight line, TS diagram.
Yes, yeah.
So the entropy at point 1 is the same at point 2. So it's 0.94467. You agree with me?
Okay, yeah.
So we're looking for the enthalpy value. So obviously at that particular point, like I mentioned to you before, the refrigerant has become superheated. So what that consequently means, we have to look at our superheated tables, which is table A13. So we locate that and we find under that pressure, right? P equals 0.8 MPa, 800 kilopascals. Are you happy with that?
Yeah, no. I'm okay now, say. Sorry.
Yeah. So
I see.
that's fine. It's good.
Yeah.
So now we have to locate where is this value, the 0.944. Obviously, it falls between this two here. So what it means, we have to interpolate between the two. So please do it on a calculator so that you get used to it. And what I'm showing you now is this is the formal process of solving the stuff. It doesn't really get too difficult. Obviously, we'll spend more time on Friday solving more of these problems. So yeah. All right, so let's see. What is my H2? So in your calculator, if you remember, Megan, do you have idea to interpolate? Because where do we interpolate before? Oh, you are doing thermal series, actually, no. Okay. I don't know how you interpolate.
Yes, sir. I got 275,4.
275,430, beautiful gents.
Okay.
275,403 kilojoules per kilogram. You do this, you get a mark there, you get a mark. Yeah, obviously. Yeah. You might even get 2 marks for this one, it depends, right? What we do now, we found point 3. Mr. Siboye likes order. I'll remove this guy. Now we process 2 to 3. And this is now our heat rejection. This is the back of the fridge, right? And what happens here, if you look at point 3, right, at point 3, you're on the liquid side. So you have to go to the pressure of 0.8 MPa on your saturated tables or 800 kilopascals and go find what H3 is. And what I mentioned to you, H3 and H4 is the same, right? We're saying it because we're saying it's an isenthalpic compression, right? In the expansion valve, right? So it means we mean isenthalpic, which means that what is this now? The enthalpy is constant, right? So this is also a pH diagram, and that's why that is there. It'll look like this, right? So pH, H is constant. You can also have this diagram if you like. Just place it here. Normally, you want to sketch one or both, depending on the object of the question. So let's go look at 0.8 on the liquid side. What am I talking about now? The enthalpy there, right? You cannot not know this. This is really 3 marks. Took my 0.8, eh? Okay, so I'll just copy this here. I can't really see, so I have to copy it here. Okay. Yep, so 800 kilopascals. What is my HF, right? Always enthalpy values. Who can find it for me there? What is my value? You should be able to read, it quick. Let's have a look. Someone say, yeah. Tinama, you're awfully quiet. Not 94.48 kilopascals. What is it, boy? There's no pressure. It's 94.48 kilojoules per kilogram. 94 point, was it 94? This guy here. Where is it? HF. 95.48, right? 95.48. Yeah, 95.48. Was everyone able to locate that one? I recommend printing these tables out. It is on Blackboard. Okay, can you guys locate it? Okay, that's fine. And also enthalpy, that means, and also that means H3 equals H4. So you probably get a mark here, and you get a mark here. It's very simple, very procedural. How many marks are we looking at already? Sorry. 1, 2, 3, 4, 5, 6 marks already. Just gotta know what is what. Are we all happy so far? And once you've done this, we've basically found everything, I think. Yep. Guys, any questions up till here before we get to the next part of the question, or when we get into the actual part of the question? I'll just wait on you guys. Hey guys, good. Can I get a few thumbs up before I proceed, please? Just so that I know everyone is on the same page. I don't really want to leave anyone behind. Okay, so the reason why I touched on the components for the analysis, obviously one needs to understand that. And I'm going to gooi this here again so everyone can see. Yeah, we're getting to the good part. Fantastic. And over here, so the question, remember the question wants the heat removal and also the power input, right? So the heat removal is QL, remember? So this is where your food is sitting and we're removing the heat. So QL is going to be mass, obviously H1 minus H4, right? Diagonal. Where's the heat removal? 4 to 1, 4 to 1, that is QL, right? At the evaporator. Now, where would what would be our compressor? Our compressor work between which 2 points is it? Which H's?
One to two.
Yes, 1, 2, 2, exactly. Child's play. So work of the compressor works WC is H2 minus H1. Unfortunately here, they've given us our mass. Sometimes you have to work out that mass, right? and hopefully I can show you how to work that out. It's not really that difficult. You have to work out the mass flow of the refrigerant, and so now we have to head back here. So the mass is 0.05, so I'm going to say QL. So this is 0.05. All we have to do is plug in our enthalpy points. So I'm the first one. So H1 was 239.19 minus H4, and H4 is 94.48. If I do the calculation there, I'll get a value of 7,91 kilowatts. That's a lot of heat. Now what you guys should do now by yourselves using the values you got, get the compressor work now, right? So use your mass flow, H2 minus H1. That mass flow rate, you can measure the expansion valve actually. If you maybe pull a flow rate flow. Yeah. So remember, your compressor work is WC or denoted, and the mass flow. I'll make a dot here. So let's get your compressor work.
Sir,
Yes, go for it.
KL is in kilowatt.
Yep. Why is it kilowatts? Remember, that's kilogram per second, right?
Oh,
And enthalpy is
mass flow
kilogram.
rate.
Yeah, it's mass flow rate, not mass. So yeah. So then obviously this is now enthalpy, and our mass flow is kilogram per second. Obviously, your kilograms will cancel, kilojoules per second, and that is kilowatts. Joules per second is watts. Yeah. So this is what we normally talk here. If we do this kind of analysis, basically depending the design, you can find out what size of compressor you need, depending on how cold you want this. Because what this means here, I will show you exactly what this is here, or the temperature of the refrigerant. So in this case, it's 0.05. H2 is 275.403 minus H1. And H1 we found is 239.19. This is straight 2 marks. This is also 2 marks. So what is that? What is you're always going to find a compressor Pooks. What does Pooks mean? 1.81 kilojoules per second. Is that your compressor? Yeah, it's correct. Yeah, 1.81 kilowatts. Yeah, 1.81 kilowatts. Okay, so we've actually managed to solve A. And now, before we get to, so that is the heat removal from the refrigerated space and the power input. So let's work out the heat rejection to the environment. And obviously, at the back of your fridge, you feel the heat there, and that is between points 2 and points 3. So we do exactly the same thing, right? So if you have a heat pump, this is what you're going to be looking at. But obviously, you guys are not aware of the heat pumps. That's perfectly fine. This is how much heat we're losing to the environment. So take 0.005. Sorry, it's H2 minus H3. H2 is always high. H2 is the highest enthalpy point on the diagram. And H2 is going to be 275.43 kilojoules per kilogram, and of course our point 0.3 was the same as 0.4. And it's, I think my laptop froze again for some. I thought the problem was resolved. Anyway, so just get QH for me quickly. Yes, I'm back. Just had obviously just froze. Do you guys manage to get your compressor work? Did you guys get it? 94,48. Sorry, that's your heat rejected, right? How much do you get for that? Hello guys, hi. You guys still with me here? Yeah? 8.99. No man. No, it means 8.99. Are you sure about that? I don't have the book in front of me. Yeah, I'll believe you there. So that's your heat rejected, right? This is heat rejected to the environment. One of the main things, again, 2 marks there. And then one of the main things is the COP of the refrigerator. And like I said, because this is not a heat pump, and what we want is the refrigerated space. So that is our output, and our input is our compressor, and it's WC. So we take QL 7.91 and we divide by 1.81, and that'll be our COP. What is my COP? Let's see, 4.37. Are you sure about that? Let's have a look. QL. So 7. So QL, right? QL should have been not your QH, QL. QL, guys. 7.91 divided by 1.81. This is 3.97. QL, remember, is the refrigerator, COP, or our output is our heat. Not, this is just our heat rejected. Don't plug and play here. 4.37 is your heat rejected. That's your heat pump. Yeah, 7.19. Sorry, I meant that. Yeah, I wrote this wrong. Yeah. Guys, any questions? This is also 2 marks. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Around 14 marks in your pocket. Do you understand why we're using QL, WC? We can initiate a small discussion, you know? Guys, is it all clear? Do you understand what's going on before I move on? You guys are awfully quiet. Seems like you know what you're doing. Okay, Mr. Blue, fantastic, guys. It's good to hear. So no questions, guys. Okay. I'm just looking at something quickly. I'm just trying to figure out where it is. All right. Where are you? Yeah, that's what I'm looking for. Okay. So we basically at the end of the first part of the lecture, and I wanted to give you guys an example to do. So we can have a break, do the example, then just go into the actual cycle and then just complete that. So we have basically 2 examples. So I'll leave you with this one here, just to practice to make sure you understand the concept. So make sure you get the answers. So it's the same concept. So guys, just looking at the example, you have particular keywords, and the keyword is ideal vapor compression cycle. So make sure you sketch your cycle. It's not actual because you're going to get into actual. And you're using R134A, that is as base. And the thing is, the condenser is at 0.8 and evaporated temperature now is at minus 20 degrees. Now, what we need is our COP and the amount of power required to service a 150 cooling load. So cooling load here is QL, right? Remember that. And amount of power, obviously, is a compressor. Right? Now, when you see minus 20, right? Remember your tables. You have to go to your other table, which is this one. So remember, there's 2 types of tables. There's table A12 with the pressures on the one side and your saturation temperatures on the one side. So you have to go to minus 20 and collect your respective properties. So I left the answers here, and I think that this should be right. It's an example in the textbook. Let me just confirm. 11:13, I think. Yeah, somewhere here. I mean, I don't have to check now. Simple work. Okay, yeah, and so just do that one. So I think we can come back in around 15-20 minutes. And yeah, make sure you just do that one. I'm gonna work through it quickly, and then we just do the actual cycle. Yeah, it's your problem 11:13 in the textbook. So I'm just doing that now. Okay, guys. So we're done with part 1, and then we'll come back for part 2. We'll solve this problem, and then we'll do the actual, and then basically conclude. And I'll probably leave you one problem for homework, which you need to actually do, or for Friday anyway. Okay, guys. I'm gonna stop recording here.